In the last section, the integral itself had something trig in it. And this section, the integral is not going to have trig in it to start with, but we're actually going to substitute a trig in. So this is trig substitution. The last section was just trig integration. And trig substitution really just comes down to three very specific suggestions for making a substitution. We've already done u substitution, where you sort of had to figure out the u yourself. Here are the three suggestions. And they say if the integral has this expression square root of a squared minus x squared in it, here's the substitution you should make. You should replace x with this stuff. And likewise for a couple others. Notice all three of them have to do with square roots. And let's go ahead and just see how this works out. I think we should jump right into an example. So let's start with this one. Let's just say find the area bounded by a circle of radius 4 in the first quadrant on the interval from 2 to 4. So first of all, let's just get a little sketch of what is going on here. So we've got circle of radius 4. Pretend that's a circle. In the first quadrant from 2 to 4. So 2 is right in the middle, 4 is right there. They want to find the area, so the integral underneath this thing from here to here, so this much. And the equation of a circle, just in case you don't remember, x squared plus y squared equals r squared. And we are probably going to want this solved for y, because our integral is going to be a dx integral. Let's see, so 16 square root of 16 minus x squared. Okay, so setting up the integral from this geometric description really isn't too hard. We just want the integral from 2 to 4 of 16 minus x squared. The doing of the integral might be a little challenging up until this point. We could try u substitution. That's probably the first thing you're going to think of. But with a u substitution, you'd make 16 minus x squared your u. Your du would need to be something like 2x. And there's just no 2x floating around out here anywhere. So let's try the trig substitution instead. The trig substitution has a suggestion. It says, hey, if you've got this form of a constant squared minus x squared, try making this substitution. So let's try that for our substitution. See how it works out. So x needs to get replaced by a sine theta. A is 4 for us. We are going to need a replacement, so we are replacing x's. So we have a replacement for x now. We're going to need a replacement for dx as well. So dx will equal 4 cosine, just cosine d theta. Just like u and du, except it's x and dx now. But okay, so let's see if we can rewrite this integral. We've got the square root of 16 is still 16, but when I substitute x for 4 sine theta, squaring that becomes 16 sine squared theta. The dx needs to get replaced by, unfortunately, a more complicated expression, but it's going to be worth it, by 4 cosine theta d theta. I'm going to leave the 2 and the 4 off for the moment. Those are x limits. There are some corresponding theta limits. I could figure those out, but I'm just at the end of this problem, I'm going to turn it back into x's, and I'll just plug in 2 and 4 when we get back to x. Okay, so this looks substantially worse than the integral we started with. And you're like, how is this going to help? But trust me. Inside the square root, notice I can factor a 16, so let's do that. See, there's a 4. That's a constant multiple. I'm just going to pull that all the way out front. There's a cosine theta there. And notice this chunk right here. That should look familiar from your days in trig. As a matter of fact, in case it doesn't, this little table here, this table's right out of the book, by the way. This little table reminds you that 1 minus sine squared is cosine squared, and it says, hey, that's what is going to come up if you make this substitution. So let's keep going with this. We'll do 4 integral 16 times cosine squared. We've got another cosine out here. And we've got d theta. Okay, all of a sudden this is looking better because both of these things under the square root, they're multiplied and they're both perfect squares, so I can just take the square root of each one of these. So I'll get 4 integral 4 cosine theta. So that's the square root portion turned into that stuff right there. Of course, we have another cosine hanging around. And with a little bit more work, I can pull another 4 out, so we get 16 integral cosine squared theta and d theta. It's still not the world's easiest integral, but we do know how to integrate cosine squared. Matter of fact, we learned that in the last section. And in case you don't recall, let's get a little room here. In case you don't recall, the idea was to use one of those identities and rewrite cosine squared as 1 plus cosine 2 theta all over 2. And the 2 on the bottom is a constant multiple. I'm going to pull that out front. So 8 integral 1 plus cosine 2 theta. And finally, this is starting to look like a somewhat doable integral. 1 integrates to theta. Keep in mind, we're still in theta here. We haven't gone back to x yet. So 1 integrates to theta. Cosine of 2 theta, you need a u substitution there. You need to make u the same thing as 2 theta. And I think, again, we're getting comfortable with that one, so I'm not going to write all of that out. But the cosine 2 theta will integrate to 1/2 sine 2 theta. And this now is still in theta. All right, and the last thing we needed to do was to plug in our limits of integration, plug in our 2 in our 4. The only problem was that 2 and that 4 are x limits. They're not theta limits. But we can change them. So back over here, let's just do that. Let's change our limits. We changed everything else. All right, so let's change the limits too. If x is 2, what's theta? So looking at this top equation right here, if x is 2, Divide both sides by 4. You get sine theta is 1/2. There are lots of places that sine theta equals 1/2, but the one that's closest to 0 is pi over 6. So that means, let's see, what do we just say? If x is 2, then theta would be pi over 6. And you can do the same thing. You can say if x is 4, plug 4 in up here. Let's see, you get 4 equals 4 sine theta. So you get sine theta equals 1. And that happens when theta is pi over 2. You might need to review your unit circle to get those. But so if x is 4, then theta is pi over 2. So our limits of integration are now pi over 6 to pi over 2. And we just need to plug those in. One half sine, let's see, 2 times pi over 2 is just pi. So there's pi over 2 plugged in, minus pi over 6 plus 1/2 sine 2 times pi over 6 is pi over 3. And we still just have a little bit of work to do as far as distributing the 8s and evaluating some trig functions. So distribute the 8, that would be 4 pi. Distribute the 8 there, that would be 4 sine of theta. Sine of theta happens to be 0. And then minus, 8 times pi over 6 is 4 pi over 3. Let's see, let me get the eraser. So distribute the 8 here. Get 8 pi over 6, or 4 pi over 3. And then sine of pi over 3. Sine of pi over 3 is square root of 3 over 2. So square root of 3 over 2. And then we had the 1/2 out front, so this is over 4. Okay, and we're basically done. I guess this, obviously that term is 0. These two terms both have pi in them, so they could be combined. Let's see, this is 4 pi, so this is 12 pi over 3 minus 4 pi over 3 is 8 pi over 3. Minus square root of 3 over 4. Final simplified answer. Okay, that was just one trig substitution. We'll take a look at another one in the next video.